When combining Internet of Things devices with XR to create immersive environments, the biggest challenge remains the localization of IoT devices with their 6 degrees of freedom for in situ visualizations. Prior work mostly manually hard-coded the device location or used image markers for a few devices. However, this is not a solution that works at scale. Others were able to locate IoT devices based on signal strength and were limited to a small number of devices distantly spread apart, and others individually toggled the device's state to identify their location, which limited them to devices that could change their state and where this change of state was easy to identify. Our system uses concept graphs to create a semantic scene graph of the room. Based on an input RGBD image sequence, we receive a semantic scene graph consisting of nodes and edges. We assume that all IoT devices are known and connected to the network and that each has network metadata. This network data has been predefined and consists of a unique name and a list of API commands that depend on the device's capabilities and allow for universal manufacturer-independent device control. Our system then combines these two data sources and maps them together, so that we know which physical objects belong to what particular network device. This way, we know precisely the 3D position and orientation of each IoT device in the room. We assume that all potential IoT device candidates have been identified in the physical objects of the semantic scene graph. And our goal is to get a bijective mapping between physical object and network device. We perform the mapping twice. We iterate over all network devices and ask a reasoning model to determine the best matching physical objects. We then do the same once more in the other direction. Afterwards, a final authoring step is required to receive the desired bijective mapping. Our introduced JSON API abstraction further allows us to automatically generate UI control panels using prefabs for every IoT device based on its capabilities. Given that the JSON data already contains the required network communication, these generated UI panels can directly control the devices on user interaction. We have evaluated our novel mapping approach and were able to reach an F1 score of 0.85 using synthetically generated rooms with randomly placed IoT devices. We've also wanted to evaluate whether the knowledge of IoT device locations can be beneficial for AR interfaces compared to a more standard interaction with a smartphone and IR remotes. To do this, we conducted a user study with 20 participants in an office filled with 28 different IoT devices. In one condition, they used our AR system, where control panels appeared right next to the devices. In the other, they used a typical setup, multiple smartphone apps and physical remote controls. The results were clear. Participants were significantly faster at completing tasks using our AR system. They also rated it as being significantly less mentally demanding, requiring less effort, and causing less frustration. The usability score for the AR system achieved 84 out of 100, compared to just 63 for the non-AR setup. Overwhelmingly, users found the AR system more efficient and fun, with one participant noting they could just find the object and change it immediately, avoiding the hassle of searching through different apps and remotes. Our system shows great promise, but we also recognize its limitations. Currently, it can't automatically distinguish between two identical lamps, which requires a final manual authoring step. We believe this can be automated in the future by combining our approach with other techniques, like analyzing wireless signal strength. The mapping from a physical object back to a network device was also less accurate, mainly because network metadata is often sparse. As manufacturers provide richer data, this will naturally improve. In conclusion, we have presented a novel end-to-end pipeline that tackles the challenge of localizing and interacting with IoT devices at scale. By leveraging semantic scene graphs and a reasoning model, we automate the most tedious part of setting up an XR IoT environment. Our unified JSON abstraction simplifies both device control and UI generation, paving the way for the practical deployment of sophisticated smart environments. This work is a significant step towards a future where our physical and digital worlds are seamlessly and intuitively integrated.